3, Graham's Law and the Purification of Gases. The following topics will be discussed in today's tutorial. Effusion and how effusion can be used to enrich or purify gas. Relating to effusion, we'll be discussing Graham's Law and going over some sample calculations, and next we'll break down the van der Waals equation and its components with a greater focus on the A and B variables. Using van der Waals equation, we will go over some sample calculations. Here we see two balloons. The balloon on the left is inflated while the balloon on the right is deflated. I'm sure we are all familiar with this process of air or helium slowly escaping the balloon through the hole in which we tie until it is flattened. Keep this idea of air escaping through this hole from an area of higher pressure to an area of lower pressure when discussing effusion. So, concept review of effusion. Effusion is a process in which gas molecules at low pressure escape from a container through a tiny orifice into a vacuum. Like the air molecules escaping from a balloon through a small space. With effusion, we assume there to be no collisions, and we remember that small molecules move more rapidly than large molecules, and that the lighter a gas is, the faster that it will fuse. This molecular weight can be determined from the periodic table. Due to the difference in molecular weight and molecular speeds, the different molecules will fuse at different rates. In the image on the screen, we see two different molecules, white and blue. As they effuse, we can see that the white molecule is effusing more rapidly than the blue at a current 3:1 ratio. Here we have two elements, hydrogen and helium. Using the concepts discussed, which gas would you expect to effuse faster? Provide a brief explanation why. You can type your answers in the chat now. If you answered hydrogen, you would be correct. So, viewing the mass of the two, we saw that hydrogen's atomic mass is equal to 1.007, and that helium's atomic mass is equal to 4.002. Even with hydrogen gases due to atomic nature, it will be the lighter molecule and therefore effuse faster. Graham's law compares the rates of effusion of two gases, A and B, under the same temperature and pressure conditions, providing us with a ratio of these effusion rates. Remember that a gas's effusion rate is directly proportional to particle movement. The faster that the molecules are moving with significant concentration, the faster the rate of effusion. On the screen, we see that Graham's law is the rate of effusion A over the rate of effusion B. So if we look over to the far right-hand side, we see that it's root MB over root MA. So we're taking the left side inversely and remembering that B is going to be over top of A on the right-hand side. We'll now be using Graham's law to calculate the ratio of the rate of effusion between ammonia and hydrogen chloride. The first step is to obtain the molar masses of the substances using the periodic table. Ammonia is equal to 17.03 grams per mole, and hydrogen chloride is equal to 36.46 grams per mole. We have the second step is to substitute the molecule's molarity into the equation and solve. So here we have rate of NH3 over the rate of HCl. So remember that B, which is going to be HCl, is over A, which is 17.03. So after calculations, we get 1.46. Therefore, the ammonia molecules effuse at a rate of 1.46 times faster than the HCl molecules. Example 2 is a little bit different. An unknown gas effuses 1.66 times more rapidly than CO2. What is the molar mass of the unknown gas? In this problem, we're using the same equation, and the first step is to again determine the molar mass of CO2, which is equal to 44.0 grams per mole. We write out Graham's equation, and then we are able to substitute and rearrange the known values. So we rearrange, and with calculations, we can determine the mass of the unknown gas, which is equal to 16.0 grams per mole. Effusion, along with other methods to be discussed another time, can be used to enrich or purify a gas. When the isotopes are unable to separate chemically through the process of effusion, the goal is to through the process of fusion, the goal is to isolate an isotope and get more of the desired one. This separation of substances purifies the substance, and this purification allows the substance to be feasible for certain uses, which we'll look at examples of. One example of purification that is seen in everyday life, not necessarily completed by a fusion, but is in large industrial facilities where emissions are purified to help limit the harm and pollutant factors. So for this example, we're looking at the purification of uranium. During World War II, scientists working on the first atomic bomb were faced with the challenge of finding a way to obtain large amounts of uranium-235. Naturally occurring uranium is only 0.720% uranium-235, whereas most of the rest, 99.275%, is uranium-238, which is not fissionable, meaning it will not break apart to release nuclear energy, and it actually is poisonous for the fission process. So uranium fluoride, UF6, has a boiling point of 56 degrees Celsius. Calculate the rates of fusion of uranium-235 F6 and 238 UF6 for a single step in which UF6 is allowed to pass through a porous barrier. The atomic mass of 235U is 235.04, and the atomic mass of 238U is 238.05. So the first step for that, we are going to calculate the molar masses of 235 and 238. So we get 349.03 grams per mole and 352.04 grams per mole. And we're just going to use this exact steps we saw before, where we write the equation, substitute the variables, and solve. Awesome. Okay, so we're going to be doing a concept review of van der Waals equation. So in order to calculate various conditions and components of a gas, we use van der Waals equation. It applies for gases under various pressure and temperature conditions. The equation below, which we see, has many variables. So nRT is going to be the pressure factor times the volume factor. P is equal to pressure, N is the number of moles, V is volume, and A and B are two new constants where A is a proportionality constant and B is excluded volume per mole. So here we're going to look at these two new variables. So A is a proportionality constant. A is the measure of strength between intermolecular forces, meaning that the higher the value of A, the more likely it is that the gas will compress. And then variable B is the excluded volume per mole, which represents the volume that 1 mole of gas occupied with when it condenses into a liquid. So we're going to go into a little bit further depth. We can see here some constants and the gas that they are with. So some of them are a little bit higher, some of them are a little bit lower, and we can see the compressibility factor. So what we're going to do is look at the A values of NH3 and helium. So NH3 had one of the higher ones on the table, equaling 4.225, while A value for helium was 0.0346, which is a lot lower. So why is this? Well, extensively strong hydrogen bonding in NH3 leads to strong intermolecular forces, resulting in high boiling point and is easily compressible. Whereas helium has only London dispersion forces, which are seen in all molecules and bonds, and they're the weakest intermolecular bond. So this results in a low boiling point and it's not easily compressible. Therefore, it has a lower A constant. So let's look at an example of van der Waals equation. So using the van der Waals equation, calculate the pressure exerted by 1 mole of diatomic chlorine gas confined to a volume of 2.50 liters at a temperature of 293 kelvins. So we got the A constant, which for chlorine gas of 6.34, and the B, which is 0.0542. So first we're going to analyze what we know. We have the number of moles, the volume, the constants, and the temperature. So we're going to calculate for n squared a and nb, as it'll be easier to put these into our equation afterwards. So for n squared a, we get 6.34 bars and liters squared, and then NB is equal to 0.0542 liters, which is the same amount due to having 1 mole. Next step is we're going to substitute the values into the equation and solve. So here we have moles, constants, everything that we saw in the slides before, and we separated the left and right sides to allow for easier calculations here. So we get on the left-hand side 9.96, and on the right-hand side we get 1.02 to give us a grand total of 8.94.